Hello everyone, my name is Salman Bawa and I have been asked to look into figure 614 in Streetman and Banerjee and investigate how it was derived from its reference, which refers to a paper that was published in 1955 by Garrett and Brattain. We will first look at figure 614 and understand the components of the space charge density per unit area, Q sub S, that forms the shape of figure 614. We will then look into how Garrett and Brattain interpreted the space charge density per unit area, fancying surfaces and a rather lengthy derivation. A link to this paper is provided in the references at the end of this slideshow. Finally, we will draw parallels between the interpretations of Garrett and Brattain and link it to figure 614 in Streetman and Banerjee. This is figure 614, and there are three important parts of this graph: the falling exponential on the left, the declining rise in the center, and the rapidly rising exponential on the right-hand side of the graph. Also note that this figure is of a p-type silicon at 300 Kelvin with doping concentration N sub A equals 4 times 10 power 15 per centimeter cube. From our assignment in the class, we know that the space charge density per unit area, also known as the surface charge, is equal to the permittivity of the semiconductor times the electric field at the surface. This gives us the final expression of Q sub S on this slide. Please note that the negative exponential surface potential phi s is a purple term, the square root of the surface potential phi s, which is the red term, and the positive exponential surface potential, which is the brown term. Plugging in the values of p-type silicon at 300 Kelvin with doping concentration N sub A equals 4 times 10 power 15 per centimeter cube, we get the final expression on this slide, which we can plot online using the MOS calculator, such that phi sub s is the x-axis and Q sub S is the y-axis. So here is our plot. The reason why you see 0.52 instead of 0.5 as the power in the expression is because the square root of negative numbers would not be plotted, and we would not get the complete graph. Now, using 0.52 instead of 0.5 has insignificant effect on the shape of the graph. However, this is not the shape we were expecting. It is quite different from figure 614. We have the falling exponential on the left-hand side of the graph and the rapidly rising exponential on the right-hand side of the graph. However, we do not see the declining rise in the center of the graph. Now, upon close examination of figure 614, we realize that the order of magnitude on the y-axis is 10 power minus 8. So, in order to verify this graph, we could do two things. Either we could zoom into the graph, or we could just focus on the terms of concern, which were the purple terms, the red term, and the brown terms. So let us simply choose to focus on the terms of concern. Focusing on the terms of concern only, we plot the blue graph. We see the falling exponential on the left-hand side of the graph, and we see what seems to be a rapidly rising exponential on the right-hand side of the graph. But still, there is no declining rise in the center of the graph. Now, since we have focused only on the terms of concern, what we have done is that we have essentially zoomed into the graph. So let us try to zoom out a bit and see if that changes our perception of the graph. So upon a considerable zoom out of the graph, we now see the falling exponential on the left, a declining rise in the center, and a rapidly rising exponential on the right-hand side of the graph. This is indeed in line with our expectations. Finally, getting rid of the square root of the non-exponential term, we plot the green graph that confirms that it is indeed this term that causes the declining rise in the center of the graph. So by simply plotting the expressions of concern in the Q sub S expression, we have verified the shape of the graph in figure 6.14. Such that the negative exponential surface potential phi s, the purple term, is responsible for the falling exponential on the left-hand side of the graph. The square root of the surface potential phi s, which is the red term, is responsible for the declining rise in the center of the graph. And the positive exponential surface potential phi s, the brown term, is responsible for the rapidly rising exponential on the right-hand side of the graph. Now let us try to get the same shape of the graph using expressions we learned from the paper by Garrett and Brattain, except that we will have to derive the expression using contemporary symbols before we can relate it back to the symbols used by Garrett and Brattain in 1955. So let us begin by using the expression for the charge density, rho of x. We then express P, P naught, N, and N naught in terms of n sub I, using Fermi level, quasi-Fermi level, and at a potential at any value of x. We then take n sub I common and get the final expression on this slide, which is equation 4 on page 378 of the journal in which Garrett and Brattain published their paper in 1955. Next, we know that the integral of the electric field from 0 to the electric field at the surface, E sub s, is proportional to the integral of the charge density with respect to the potential from 0 to the surface potential phi sub s. Inserting the expression for the charge density, rho of x, and taking n sub I common, we get this expression. Upon integrating both sides, we get the final expression on this slide. We then take kT upon Q common and then rearrange the expression, which helps us in getting our three major terms inside the brackets: the falling exponential, the rising exponential, and the phi sub s terms. We then bring n sub I back into the brackets to get the final expression on this slide. We then express the quasi-Fermi level in terms of the Fermi level and the quasi-potential of holes and electrons. We then get the brown, blue, and the green terms, which are the terms for P0 and N0. We then divide the entire expression with n sub I to get the final expression on this slide. Okay, now note the brown, blue, and the green terms. And now note how these terms get encrypted into the symbols of 1955. In particular, note that lambda is the ratio of P0 to n sub I. Hence, it is a measure of whether the semiconductor is p-type or n-type. Capital P is the positive potential due to the quasi-Fermi level of holes. Capital N is the negative potential due to the quasi-Fermi level of electrons. And Y is the surface potential expression Q over KT times phi sub S. Then we take 2n sub I from the denominator of the left-hand side to the numerator of the right-hand side of the equation. We then take the square root of the entire expression to get the surface electric field, which is the expression on this slide, the last expression on this slide. And it is also the equation 6 on page 378 of the journal in which Garrett and Brattain published their paper in 1955. Note that we have a new term, a fancy looking L, which we call the characteristic length of the semiconductor. This is equal to the square root of 2 times the Debye length of the same intrinsic semiconductor. Now we know that the surface electric field is the ratio of the change of surface potential with respect to the distance or depth into the semiconductor from the surface. Hence, d phi sub s by dx. We then take KT over Q from the right-hand side to the left-hand side of the equation, giving Q over KT times d phi sub s in the numerator of the left-hand side of the equation. But according to the encrypted symbols of 1955, Q over KT d phi sub s is dy, giving us the final expression on this slide. In 1955, Garrett and Brattain were inspired by the works of J. Willard Gibbs, who in 1906 explained surface excesses of electrons and holes. In order to make a Gibbs expression for excess holes and electrons finite, Garrett and Brattain had to change dx to dy. And hence the integral of dx by dy with respect to y, which is the potential from 0 to the surface potential capital Y, is indicative of the shape of the space charge region. Now, since dy by dx is this expression which is on the slide, dx by dy is the inverse of that expression. And so we get an expression for x in terms of an integral of y, which is the potential, and this becomes the final expression on this slide. Now, Garrett and Brattain did not solve the integral further, but simply used it to interpret the shape of the space charge region. So for small values of y, which is the surface potential, only 1 over y dominates the term inside the integral. And since the integral of 1 over y with respect to y equals ln y, it implies that the shape of the space charge region follows a logarithmic shape, which is consistent with the square root of phi sub s term. For negative values of y much less than -1, e to the power minus y dominates the term inside the integral. This integral gives us the falling exponential shape of the space charge region, consistent with the negative exponential surface potential phi s term, which is the purple colored term on this slide. For positive values of y much greater than 1, e to the power y dominates the term inside the integral. This integral gives us the rapidly rising exponential shape of the space charge region, which is consistent with the positive exponential surface potential phi s term, which is the brown colored term on this slide. Now recall that lambda is a measure of whether a semiconductor is p-type or n-type. Also note that e to the power y term is linked to lambda inverse in the expression, hence an indication of a rapid rise of minority carriers close to the surface of the semiconductor, such that the semiconductor acts as its opposite type at the surface compared to its type in the bulk. This is called the inversion region. It is very interesting to note that Garrett and Brattain concluded this without actually ever plotting the graph of figure 614 in their paper of 1955. So the conclusions drawn from the 1955 paper of Garrett and Brattain and figure 614 are as follows. For an n-type semiconductor, when lambda is less than 1 and the surface potential is large and positive, space charge region is accumulated with majority carriers, accumulation of electrons. When lambda is less than 1 and the surface potential is small and negative, space charge region is exhausted of any carriers. This is the depletion region. And as the surface potential increases in negative, minority carriers, in this case the holes, may show up in the space charge region. When lambda is less than 1 and the surface potential is sufficiently large and negative, space charge region is inverted with minority carriers. This is the inversion region, with excess holes at the surface of an n-type semiconductor. Similarly, for a p-type semiconductor, when lambda is greater than 1, and surface potential is large and negative, Space charge region is accumulated with majority carriers, accumulation of holes. When lambda is greater than 1 and surface potential is small and positive, space charge region is exhausted of any carriers. This is the depletion region. And as surface potential increases in positive, minority carriers, in this case electrons, may show up in the space charge region. When lambda is greater than 1 and the surface potential is sufficiently large and positive, space charge region is inverted with minority carriers. This is the inversion region with excess electrons at the surface of a p-type semiconductor. All right, so what are some of the lessons learned? First, it's the link between Garrett and Brattain's 1955 paper and the figure 614 in Streetman and Banerjee. And we looked at the links in the previous slides. Personally, for me, I learned a lot about Brattain as a person. There is in fact a memoir written by Brattain for Brattain, and I have put that in the references. And through that, I was able to learn a bit about the history and the time in which the 1955 paper by Garrett and Brattain was written. And essentially the journey of the three forks, Brattain, Bardeen, and Shockley, who won the Nobel Award in 1956, the journey of these three people starts in and around 1947, when Shockley gave Brattain and Bardeen the work to look into why a prototype of a transistor was not working in Bell Labs. And Brattain and Bardeen, while investigating into that transistor, eventually came up with the point contact transistor in 1947. And this is what they presented to a team of scientists and researchers in Bell Labs. What happened after that was that Shockley was disappointed, in fact very angry, that Brattain and Bardeen never mentioned Shockley's name while they did that presentation in Bell. So Shockley told Brattain and Bardeen that he would be working on a different kind of transistor, which he called the junction transistor, and that he involved lawyers in Bell to make sure that Shockley's name goes into this particular type of transistor, which is the junction transistor. And that's what caused what commonly came to be known as the Shockley's rift with Brattain and Bardeen in Bell Labs. And over time, this animosity just kept on growing and became very prominent in Bell. And in fact, in 1951, Bardeen decided to leave Bell, citing a toxic environment as his reason. And Brattain and Garrett then wrote this paper in 1955, and I am suspecting that given this toxic environment, given this highly competitive nature, kind of a rift between a boss and an employee, where Shockley was heading this Bell Labs at the time, I am suspecting that it may be the reason why in the paper in 1955 Brattain and Garrett did not go into the depths of explaining the expressions for the surface charges. It's quite possible, but it is my suspicion. And in 1956, Shockley left Bell to start a company in Silicon Valley, which apparently became the first semiconductor company in Silicon Valley. And in 1956, the same year, the three men receive the Nobel Award for Physics. And you can imagine at this time, none of them were in talking terms. So Brattain and Bardeen were still talking to each other, but between Brattain and Bardeen and Shockley, they were not talking. In fact, in 1956, when the three were called to give presentations at the Nobel Award ceremony, each of the person gave separate presentations. Now, a point to note here is that Bardeen went on to win the second Nobel Award in 1972. So I'm assuming that the environment in Bell at the time, during these times, were pretty toxic. In fact, there's a paper in the reference that names Shockley as the second most controversial figure amongst scientists, and the top position for that is held by a psychologist. Anyways, moving on. It was in 1959 that Atala and Kang in Bell Labs invented the MOSFET. And the MOSFET, as we know, makes a use of the inversion layer, the buildup of the charges in the inversion layer, and then the potential difference between the source and the drain that causes the flow of charges through a channel. And it was in 1967 that Brattain retired from Bell Labs. So it was very interesting for me to understand the scenario and the stuff that was actually going on during these times that led to the paper of 1955 and eventually the invention of the MOSFET. Here are the references, and thank you very much for listening to this video presentation. I would have loved to do this live in person, but we all have to play our role in flattening the curve for COVID-19. So thank you very much, and stay safe, stay healthy. Thank you.